Welcome back to Dr. Liu's VCE Biology. Today's topic is human change over time and scientific investigation, as presented in the 2024 NHT Biology exam. Let's learn together. If teachers, parents, or students notice mistakes in my explanations, please provide me with your feedback. In another unrelated Quoll study, scientists recorded the seasonal activity of a population of a different species of quolls in the Illawarra Highlands in NSW. The activity of the quolls was recorded by taking photographs. The number of photographs taken was recorded at 3 different times each day throughout the study. Data from the study were arranged by season. Quoll activity levels shift throughout the year. During summer, they are most active in the daytime, while in autumn, they prefer to be active at night. Their daily habits vary significantly between day, night, and dusk. In spring, they show the least activity at dusk or in the morning, with similar activity levels during the day and night. Of all seasons, quolls are most active in winter. Fieldwork is employed to study the highland quoll population, as it allows for the collection of data that better represents their behavior in their natural habitat. Achondroplasia is the most common cause of dwarfism. It is caused by overactivity of the FGFR3 receptor. A new drug, vosoritide, blocks the activity of the FGFR3 receptor and allows for normal bone growth. Trials have confirmed that vosoritide is safe to give to young people with achondroplasia. To have the greatest effect, vosoritide is given as a daily injection from birth. The Australian government has subsidised the cost of the drug so that it is more easily available for those who choose to use it. A virtues-based approach focuses on the moral character of the individual. It suggests that by practicing virtues like honesty and compassion, a person will naturally act in the right way. A duty-based approach, deontology, asserts that certain actions are inherently right or wrong, regardless of their outcomes. The core principle is that it is a moral duty to act in accordance with universal moral laws, and that causing harm is never acceptable. A rule-based approach is a decision-making method that uses a predefined set of instructions, often in the form of if-then statements, to guide actions and reach conclusions. A consequences-based approach, consequentialism, evaluates the rightness or wrongness of an action based solely on its outcomes. The core principle is that an act is morally correct if it produces the best overall results, meaning it maximizes positive outcomes while minimizing negative ones. Considering that this study aims to achieve maximum positive outcomes with minimal negative effects when administering vosoritide, the ethical approach is identified as consequences-based. After completing their research, scientists must honestly report all information and results, regardless of whether they are favorable or unfavorable. This practice aligns with the principle of integrity, which refers to the quality of being honest and having strong moral principles. It means consistently acting in accordance with those principles, even when faced with difficult situations or potential personal gain. Based on the evolutionary tree, Australopithecus anamensis is positioned before Australopithecus afarensis on the same lineage. This arrangement indicates that A. anamensis is a likely ancestor of A. afarensis. The fossil record for hominins is incomplete, which means some species may be absent from it. Furthermore, the limited nature of some fossil finds, such as a single finger bone, can make it challenging to compare species and infer relationships. Finally, the close physical similarities among certain Homo species can make it difficult to determine their precise evolutionary relatedness. As the genus Australopithecus evolved into the genus Homo, several key changes occurred. The cranial size increased, while the size of the brow ridges and jaw was reduced. Additionally, the face became flatter, and the leg-to-arm ratio became longer. There is evidence that Denisovans and Neanderthals interbred. DNA evidence also shows that Homo sapiens interbred with Neanderthals in Europe, and with Denisovans in Asia and New Guinea. Scientists who have mapped the genomes of people of the islands of Southeast Asia have found that 3% to 5% of their DNA can be traced to Denisovan ancestors. Based on differences in their genomic DNA, 3 separate populations of Denisovans have been identified. The first Denisovan population, D0, was first discovered in fossils found in Siberia. The second Denisovan population, D1, is thought to have split from the D0 population around 283,000 years ago. The third Denisovan population, D2, split from the D0 population around 363,000 years ago. The D1 genome is distinctly different from the D0 genome. The D1 population genome sequences are especially common in the indigenous people, Papuans, of the island of New Guinea. Both Papuans and Aboriginal and Torres Strait Islander peoples have relatively high levels of Denisovan DNA in their genomes compared to other H. sapiens populations. Current evidence suggests that Aboriginal and Torres Strait Islander peoples have been living in Australia for around 65,000 years. There is no current evidence of Denisovans having lived in Australia. Up until 10,000 years ago, Australia was joined by a land bridge to New Guinea and known as Sahul. A group of scientists hypothesized that the Denisovan population had been living in New Guinea and, isolated from other Denisovans, had reproduced with H. sapiens sometime between 15,000 and 30,000 years ago. A second group of scientists challenged this hypothesis. This group of scientists suggests that Denisovans reproduced with H. sapiens much earlier than 30,000 years ago. Modern populations on the islands of Southeast Asia have inherited 3% to 5% of their DNA from Denisovan ancestors. The proportion of Denisovan DNA found in different human populations can be used to determine the timing of interbreeding events or population splits from common ancestors. The D1 population diverged from D0 approximately 283,000 years ago. Over time, different selection pressures led to significant evolutionary changes in the D1 lineage. In contrast, D2 and D0 split about 363,000 years ago, and because they likely experienced similar selection pressures, their genomes accumulated only minor changes. Despite the lack of Denisovan fossil evidence in Australia, the presence of Denisovan DNA in Aboriginal genomes suggests a different timeline. This genetic evidence supports the hypothesis that the interbreeding event happened outside of Australia, likely in Southeast Asia, before these ancestral populations migrated to the continent over 65,000 years ago. The incompleteness of the fossil record and the potential for new discoveries mean that other explanations remain possible. For instance, the presence of Denisovan DNA in Aboriginal Australian populations could be explained by interbreeding that occurred within the Australian continent, rather than before their arrival. This section, Human Evolution and Scientific Investigations, is worth 18 marks and contributes to 15% the total 120 marks. Multiple choice questions, 4 marks, question 32 and 33, Quoll and Fieldwork. These questions will test how fieldwork is used to study animal behavior in its natural habitat, and how observational data reveal seasonal activity patterns. Question 39 and 40, Ethical Approaches. You'll need to apply consequences-based ethics to a scenario, showing you understand how this approach focuses on maximizing positive outcomes while minimizing negative ones. Short answer questions, 14 marks, question 9, Human Evolution and Fossils. This question is about the limitations of the fossil record. You should explain how a lack of complete fossils, the fragmentary nature of samples, and the physical similarities between species make it difficult to determine evolutionary relationships. Question 10a. Explain how the presence of Denisovan DNA in modern humans provides evidence of interbreeding, even without fossil records in some areas. Question 10b and 10c. Use the Denisovan D1, D0, and D2 populations to show how genomic differences can reveal past selection pressures and evolutionary divergence. Question 10d. Consider how new fossil discoveries or the possibility of interbreeding within Australia could change our current understanding of Aboriginal migration history. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.